Now I'm going to compute the vertical asymptotes of several rational functions, and I'm going to do it quick and dirty. And that means I'm not going to laboriously check limits at all of the places where I think there's going to be a vertical asymptote. I'm going to use this trick or this hack. So for any rational function that I get, what I'm going to do is first I'm going to cancel out any common factors that there might be in the numerator and denominator. Normally I would not be allowed to do this. It might change the domain, it might mess up the graph. But because we're talking about asymptotes, because we're talking about limits, I'm allowed to do this. After I'm done with that, I'm going to set the denominator of the function equal to 0, and I'm going to solve it. And those solutions are going to tell me exactly where the vertical asymptotes are. For example, I'm going to find all of the vertical asymptotes of this function, x minus 2 divided by x minus 2 times x plus 5. Notice we have a theorem that says that this function will be continuous at all real numbers except for positive 2 and negative 5. So I know that these are the only two possible places where there could be a vertical asymptote. And I also know that these two places, 2 and negative 5, will be one of two things. They are either going to be an asymptote or they're going to be a removable discontinuity. Now notice that this function, if I cancel out those common factors, I know that this function is equal to 1 over x plus 5, except when x equals 2, right? Well, that means that x equals minus 5 is a vertical asymptote, and it means that x equals 2 is a removable discontinuity. So a couple of other facts just to help you understand why this works the way that it does. Here's the two-sided limit as x approaches 2 of this function. You get to cancel out the common factors on top and bottom because you're computing a limit. So you get the limit as x approaches 2 of 1 over x plus 5. Then you get to use the direct substitution property. So that limit is literally equal to 1 over 7, which means no vertical asymptote. Pro tip, this means that you cannot assume that every root of the denominator that you see will correspond to a vertical asymptote. You do not get to make that assumption. Here's another piece of information for you. Here's the graph of the function. And I hope you can see that this graph does exhibit that crazy steep behavior over at x equals minus 5, and it does not exhibit that crazy steep behavior at x equals 2. And so definitely there's only one vertical asymptote here. Here's my second example. This is a pretty complicated looking function, x minus 1 squared times x minus 2 over x minus 1 times x minus 2 squared, and I want to know where the vertical asymptotes are. Straight up, right away, I know that g is continuous everywhere except for positive 1 and positive 2. So those two places are either bubbles, removable discontinuities, or they are vertical asymptotes. Now when I do that first step that I talked about, I cancel all the common factors on top and bottom. I can cancel one copy of x minus 1 from top and bottom, and one copy of x minus 2. So that means that g of x is equal to x minus 1 over x minus 2, with the exception of when x equals 1. And I hope you can see that if you were to plug in x equals 1 into the original formula, you would get 0 over 0, which is undefined. Therefore, x equals 2 is a vertical asymptote, x equals 1 is a removable discontinuity. This problem is over. So if you were to analyze this function with a table of values, you would find out that from the right, the limit as x approaches 2, from the right of this function is actually positive infinity, and the left-hand limit as x approaches 2 of g of x is equal to negative infinity. And if you remember the fancy formal definition of what a vertical asymptote is, this is what it means to have a vertical asymptote at 2. Pro tip, you cannot assume that if a factor cancels out from numerator and denominator, then that factor will lead to a removable discontinuity. You might be fooled into thinking that because we were able to pair up and cancel copies of x minus 2 from top and bottom, then clearly there must be a bubble or removable discontinuity in the graph. That turns out to be completely false. So here's the graph of the function. It's equal to x minus 1 over x minus 2, which has a 1 over x type shape. Except when x equals 1, there will be a removable discontinuity or a bubble in the graph. And again, you can see this lovely steepness. There's a vertical asymptote right here at 2, but there is not one over here at 1. My final example, I want to find all vertical asymptotes of h of x equals x cubed minus 8. And you can see that linear factor on the bottom, and you're like, ooh, maybe x minus 2, maybe x equals 2 is an asymptote. But up top, it's kind of hard to tell that x minus 2 might or might not be a factor. Well, you don't get out of the work here. You have to do the work of factoring out that polynomial as much as you can. And here's a tiny hack, something that you can do. Simply try to plug in the number 2 up here. If you get 0, that means that x minus 2 is a factor of that polynomial. So there's a little trick for you to use if you can remember it. And so if you were to factor out an x minus 2 from this polynomial, then what's left over is x squared plus 2x plus 4. So okay, I'm ready to proceed. H is continuous at all real numbers except for x equals 2. So that means there can only possibly be one vertical asymptote and maybe not even one. This function is equal to x squared plus 2x plus 4 except when x equals 2. And so that means that this shape of this graph is a parabola of some kind with a single removable discontinuity in it. It's removable because I canceled out the only x minus 2 factor that was in the denominator. So there's only one removable discontinuity and there are no vertical asymptotes at all. So beware. Just because you don't see the factor right away on top and bottom, you may have to factor out the numerator or the denominator. You might have to do other types of algebra in order to get the function in the right form in order to use this handy technique. Finally, here's that graph of h. It turns out to be a parabola and it has a single removable discontinuity. And I think that you can see there is no place on the x-axis where this function displays the kind of steepness that would make us say that there's a vertical asymptote.